Hello everyone, welcome to this video. This is the third video of basic set theory. We are going to study several basic set operations. We use set operations to generate new sets from given sets. The first operation we are going to learn is the intersection of two sets. The intersection of two sets A and B, denoted by A intersects B, is the set containing all elements of A that also belong to B. Or in other words, the intersection of two sets is a set that contains elements from the both sets. For example, here we are given two sets A and B. To get the intersection of A and B, we need to find their common elements, which are 5 and 9. To visualize this process, we could draw two circles representing set A and B. Elements of a set reside inside the circle. So the common area of the two circles are those elements belonging to both sets, 5 and 9, which composes the intersection of A and B. This part of the diagram represents elements that only belong to A, which are 2, 4, 6 and 8. And similarly, this part of the diagram represents elements that only belong to B, which are 1, 3 and 7. The diagram we are using here is called Venn diagram, which is named after a British mathematician. We will see by visualizing set operations, Venn diagram turns out to be very useful in solving problems involving set operations. Let's do two exercises about intersection. First, we are given two sets X and Y. X contains letters in the word mathematics. Y contains letters in the word set theory. To easily find their common elements, we could list all their elements separately. Remember that repeat letters should appear only once, since a set cannot have repeat elements. X contains elements M, A, T, H, E, I, C and S. Y contains elements S, E, T, H, O, R and Y. Their common elements are T, H, E and S, which are elements of the intersection of the two sets. In the second problem, we are given three sets R, S and T. R contains all integers that are divisible by 2, or in other words, all even numbers. S contains all integers that are divisible by 3. T contains all integers that are divisible by 6. Let's first consider R intersects S. There are integers that could be divisible by both 2 and 3, which means they should also be divisible by 6. So the intersection of R and S contains integers that are divisible by 6, which is set T. Now let's consider R intersects T, and S intersects T. If you have watched the previous video of this series, you might remember T as a subset of both R and S, which means every element of T is also in R and S. This is not too difficult to see since any integer that is divisible by 6 is also divisible by 2 and 3. So every element of T is a common element. Then R intersects T and S intersects T both equal T. The second operation we are going to learn is the union of two sets. The union of two sets A and B, denoted by A unions B, is the set containing all elements from both sets. Here we have used Venn diagram to visualize this definition. The union of two sets A and B covers all areas of both sets. For example, given the two following sets, we write elements from both sets to construct their union, which are numbers 1 to 9. Again, when constructing the union of two sets, elements that belong to both sets should appear only once. Let's do our exercise involving letters again, but this time we need to find the union. Instead of finding letters that are common to both sets, every element in either set should appear in the union. So the elements of X unions Y are M, A, T, H, E, I, C, S, O, R, and Y. In the next exercise, we are given the sets R, S and T. This time we need to determine R unions S, R unions T, and S unions T. The union of R and S contains elements that could be divisible by 2 or 3. And as mentioned before, T is a subset of both R and S, which means its elements are already all in R and S. So R unions T should equal to R. And S unions T should equal to S. Now let's show the relation of these three sets in a Venn diagram. From this problem and the problem in the earlier exercise we have known T as the intersection of R and S. So we could draw two circles representing R and S, then their intersection area is set T. We could see directly from the diagram that R unions T equals R. And S unions T equals S. Two sets could also be subtracted, which is the third operation we are going to learn. The difference of two sets A and B, denoted by A minus B, is the set containing all elements of A that are not in B. Or in other words, we obtained set A minus B by deleting common elements of A and B from A. The difference of two sets could also be written like this. A minus B is also called the relative complement of B with respect to A. In the Venn diagram, A minus B is the area only belonging to A, and B minus A is the area only belonging to B. For example, for the given sets A and B, A minus B contains 2, 4, 6, and 8. And B minus A contains 1, 3, and 7. Back to our letters example, by the definition, we could easily get X minus Y contains M, A, I and C, and Y minus X contains O, R and Y. Sometimes mathematicians refer to a set called universal set, denoted by U, which is a set containing all elements of current given context. For example, if we are dealing with problems of integers, the universal set might be the integer set Z. But if we are dealing with a geometric problem, the universal set could also be all possible closed shapes in a plane. Since the universal set contains all elements we are interested in, it contains all other sets. For a given set A, U minus A is also called the absolute complement of A, or simply the complement of A. And it has another notation like this. For example, for our set R from previous exercises, the even number set, if the universal set is the integer set Z, then U minus R is the odd number set. In a Venn diagram, the universal set is usually represented by a rectangle, in which we draw all other given sets. Until now we have learned three basic set operations: intersection, union and difference. The last thing I want to mention in this video is we could combine these operations to get more complicated expressions of sets, which are called set algebra. Here is a simple example of such expressions. It gives the difference of set A unions B and set A intersects B. If A and B are shown in Venn diagram like this, we need to eliminate the area of A intersects B from the area of A unions B, so the resulting set covers the area that only belongs to A or only belongs to B. When we mix different set operations together, we could use brackets to show the relative priority of them. When there are no brackets, we just calculate from left to right by default. We will see more examples like this in the next video. Here are recap shots about this video's content, you might find it useful somewhere. If you find this video helpful, please subscribe, like and comment below. Thanks for watching and have a good day.